Again?
Hello, I'm Ajay Kumar Kushwaha. I'll be presenting a paper, Golmaal, thanks to secure TimeCache for a faster DRAM code channel. My co-authors are Ajay Jain, Mahindra Patel, and Biswabandhan Panda. We are affiliated with the Department of Computer Science and Engineering, IIT Bombay. This is a fun conversation between an attacker and a defender. The attacker brags to the defender that he can perform plus reload attack. To counter, the defender suggests using TimeCache. The attacker sarcastically acknowledges the defender's intent to send first access to a cache line for each process to the DRAM by creating a miss, thereby eliminating the flush plus reload attack. The defender looks happy. The attacker further rhetorically remarks, wouldn't this eliminate the need of CL flush required by the code channels in DRAM, increasing the total bandwidth? Let's get some familiarity with the background knowledge required to understand the Golmaal code channel. Row buffer conflict code channel. The sender and receiver processes agree on a bank in a channel. They decide on different rows in this bank. The receiver will continuously access its row. Repeated access by the receiver ensures row buffer hit, that is faster access. The receiver interprets this to be 0. When the sender wants to send 1, it accesses its own row, causing a row buffer conflict for the receiver, giving slower access time. This is interpreted as 1 by the receiver. Let's see this through an illustration. Here, the sender and receiver agree on different row in the same bank. Green is the sender and orange is the receiver. As an initialization step, when the receiver accesses its row, it gets a row buffer miss, as the row buffer contained garbage value. By repeatedly accessing the same row, receiver gets row buffer hit, hence low access time. If the sender accesses its row, it leads to a row buffer conflict for the receiver and high access time to it. By using this mechanism of low and high access time, sender can send 0 and 1 bit respectively. Time cache. In a flush plus flush reload attack, the spy flushes a cache line that he suspects is used by the victim. Later, he measures the reloading time to this cache line, inferring whether the victim has accessed the suspected cache line. Therefore, the first access time measurement is important for flush reload attack. To counter this, the time cache dictates that for each process, the first access to a cache line should be a miss, even if the cache line already exists. SBIT is used to track if it is the first access of a process to a cache line. Let's assume a cache line of interest is already in cache, and SBIT is set for both spy and victim. The spy flushes this address, resulting in the SBIT for this cache line to be unset for both spy and victim. Now if the victim accesses the cache line, it will be a miss. DRAM will return the cache line and the SBIT of the victim will be set. If the spy reloads now, it will encounter a miss irrespective of the whether victim has reloaded or not, since the spy bit is not set. The request would be sent to the memory, and when served, it will be discarded. To further understand Golmaal covert channel, we have divided our slides into 4 sections: assumptions and protocol, timing diagram, transmission channel, and evaluation. Golmaal channel, covert channel has some assumptions. Let's start with theoretical assumptions. Shared memory agreement. Here we assume that multiple senders can share memory among them, hence can be allocated the same DRAM row. Similarly for the receiver. We also assume senders and receivers can be allocated different rows in same bank, rank, and channel. We also make the below numerical assumptions. We have acquired them from various credible sources. To introduce our protocol, this diagram represents machine with 8 core 16 thread processor. We have 8 receivers from R1 to R8. Similarly, there are 8 senders from S1 to S8. Receivers are mapped to address A1 and senders are mapped to address A2. We must ensure that A1 and A2 are mapped in different rows, namely R2 and R4, but within the same bank, rank, and channel. Timing diagram. Let's see the advantage Golmaal has. In the traditional code channel, first we must flush address A1 and then receiver 1 can address access A1. Similarly, if receiver 2 has to access A1, it requires the address to be flushed. Otherwise, it would get a cache hit and not reach DRAM. So, alternate flushing and loading are required. But in the case of Golmaal, after the initialization step, subsequent receivers won't have to pay for CL flushing address A1, as it is their first access to it after it has been loaded. So each load would directly go to the DRAM. This would continue until we exhaust all the receiver process. Then we have to restart the whole sequence. In comparison, we can see the Golmaal code channel can potentially transmit twice the amount of bits in the same period. Transmission channel. Let's see how bits are transmitted when time cache is used. The first step will be initialization if the row buffer contains a garbage value. Receiver R1 makes an access to address Y. Since S bit is 0, time cache treats it as a miss. This will further create a row buffer conflict. But eventually, the row buffer will be set to the row containing the address Y, that is B. Also, the S bit of the R1 will be set. If 0 is to be transmitted, the sender will do nothing. R2 will access the address Y. As its ASP bit is also 0, it will cause a cache miss but a row buffer hit. R2 will interpret this row buffer hit, that is low access time, as 0. In the end, S bit for R2 will be set. If 1 is to be transmitted, the sender will access the address W. Eventually, the row buffer will contain the row that has sender's address W. S bit for S1 will be set. Later when R3 accesses address Y, as its S bit is also 0, it will cause a cache miss and a row buffer conflict due to sender's previous activity. R3 will interpret this row buffer conflict, that is high access time, as 1. Evaluations. We simulate our covert channel with an extensively modified Champion simulator. We also use RAMulator, DRAM simulator, and merge it with Champion for detailed simulation of DRAM timing constraints. We use DDR4 DRAM with a data rate of 3200 megatransfers per second. For synchronization, we use wall clock time and 100 nanoseconds of sleep after every DRAM access by a sender and a receiver. We evaluate our code channel with various data sequences. The sequence of all zeros give higher bandwidth as they only consist of receiver with row buffer hits, therefore get highest raw bandwidth of 6.82 Mbps for all zeros. On the other hand, the sequence of all ones contains sender and receiver loading their addresses alternatively. Therefore, the bandwidth is lowest of all of 4.53 Mbps. To calculate the average bandwidth, we generate and simulate 10 random sequences. Then average them to get a 5.88 Mbps bandwidth. We also observe that as we increase the number of senders and receivers, bandwidth also increases with it. To calculate the error percentage in our channel, we transmit the data containing all ones. This means the sender and the receiver load alternatively. If anytime receiver loads one after the other, it gets a row buffer hit, that is 0. So each 0 is an error. For this sequence, we encounter the maximum error percentage of 12.8 at 4.28 Mbps. Similarly, we calculate the through capacity for the same sequence and get a maximum bandwidth of 3.72 Mbps. Lastly, we want to thank DRAM for providing us the opportunity to present our paper. We also want to thank anonymous reviewers for providing us with a constructive review and feedback. Thank you all so much.
All right, great. Thanks for the presentation. And I will see whether there are questions. Please either raise your hands or type it in the chat channel. And while I give some time for others to ask questions, maybe I can ask the first question. So this is so I find it interesting, right? Because people are, of course, coming with a lot of mitigations to sort of fix some, issues inside the CPU. But of course, sometimes this exposes potentially other attack surfaces, let's say on other part of the system, such as DRAM. And this is interesting. So you looked at covert channels, but I was just wondering whether, for example, you could also use the same mechanism to improve, for example, rowhammer attacks.
As rowhammer also uses repeatedly access to row lines, so repeated access of this would require CL flush, right? And, yeah. So if you avoid the CL flush and you can have more of the, more data, more accesses, that could lead to more improvement in that rowhammer.
Cool. Do we have maybe another question? Okay, if not, then let's thank our speaker, and we can move on to the next.